All right, we got another torque problem. So since this one is in rotational equilibrium, we know that the net torque equals 0, which means counterclockwise has to equal clockwise. So these two things are dragging it down this way. This one's dragging it down that way, but they must be bound. They must have the same torque. All right, so we have the torque of M1 plus the torque of M2 must equal the torque of M3. So we have the RF of 1 plus the RF of 2 has to equal the RF of 3. Now, what is the force? Okay, well, we've got mg down and some tension going up. So the force is mg. So R of m1g plus the R of m2g equals the R of m3g. Now, actually, the g's all cancel out. So if you forget the g, technically you're fine, but I will judge you if you don't write it. So the distance is the distance from the fulcrum. So this distance for M1, that's 4, 5, 6, 7. We'll call that 0.7 meters. And the mass of M1 is 3.39. The distance for M2 is 0.4 meters, and his mass is 8.16. The distance for this one is 0.3. You don't have to worry about negatives or positives. It's just like how far is it? What's the distance? And we don't know M3, but one equation, one unknown, we can do this. So 0.7 times 3.39 plus 0.4 times 8.12 divided by 0.3. I got 18.79. 18.79 kilograms. So that's how you do torque problems.